Okay, so today is the last day, last lecture of this Spintronics class. So instead of explain more details of some specific technology, I want to give a brief explanation of the future of the Spintronics development and the current state also. Okay, so after this short lecture, we're going to have some chance for the questions from students. Okay. So, yeah, since I explained many things about the spintronic devices, including GMR, TMR, spin transfer torque, and also I briefly explained about the spin orbit torques. So, in the current state of the spintronics is we are using this technology in magnetic sensors, many kind of magnetic sensors. Which one is existing in maybe in your smartphone and also your car and many things. And also, hard disk drive, we are using that kind of technology. But the hard disk is kind of the shrink down business because of the solid state memory. The hard disk market is going getting smaller, and they replaced by the solid state memory. Even for the large amount of the storage, like data center. In a data center, they have a really huge capacity of the memory. So people build up by that kind of data center with hard disk drive, but they found the cooling cost is really expensive. Sometimes the cost for the hard disk drive and the building is less than the cooling power cost. So some people claim that if we replace hard disk drive with the solid state memory, even the initial cost is higher, but eventually the maintenance and the maintenance cost is much lower. So eventually it's more advantageous. So many data centers start to replace hard disk drive with the solid state memory. Yeah. And also, I explained many things about the spin transfer torque RAMs, but so far I explained only a standalone memory system. The standalone memory means they are using the memory as a just main memory of a computer, or just to store the data, like a DRAM or flash memory. But that kind of standalone memory requires very high density and high capacity. So it's not market. Actually, they can make it commercially, but the problem is there's no when they competed with the existing memory like a DRAM or flash memory, MRAM is not quite benefit. There's no good advantage. But in other kind of memory called the embedded memory, it's already commercialized. The embedded memory means the memory is embedded in other kind of circuits like main memory and the CPU, like as a cache memory, or in kind of graphic card memory and some such kind of things. So compared to the standalone memory in the market in 2018, it's around $300 million. When we predict the market is getting larger, and after 3 years, we will have a 6.1 billion market. And for the embedded memory, and this year, it's much smaller, like only a few percent. But in this year, this market is getting bigger. So they predict the spin transfer torque MRAM make a big market, and if we success to make the embedded memory, and then there's a many bright future. And the good thing is, embedded memory, the requirement condition compared to the standalone memory is much easier. So that's why they can commercialize embedded memory first. But the problem is, in embedded memory, they should making the chip with the logic gate, not only the memory. So like a CPU or some kind of a APU. So they require a lot of technology, not only the memory technology, but also the logic technology. So actually, in Korea, Samsung and Hynix, they are very strong in a standalone memory. But in embedded memory, they are very weak, especially in Hynix. They cannot make any embedded memory. They focused only the standalone memory. So the Samsung and Hynix investigated a lot for the STM NAND, but Samsung successfully commercialized the embedded one. But Hynix, they cannot make the embedded memory, so they still try to make the standalone memory. So here is the list of the future promising technologies for the Spintronics applications. Like SOT memory called the spin-orbit memory is another word. It's called the memory in logic. I'm gonna explain it later. And Scomonics means using the Scomion as an information carrier, and then we can build up any kind of the memory and also logic gate, and even for the neuromorphic applications. And for the magnonics, they based on the spin wave, so it's quite similar to the photonics. And there are many advantages in magnonics, but still it's just earlier stage. It's just the first stage, so there are so many things we have to solve it. And also there is a very exotic material called the topological insulator. And then when we attach the ferromaterial layer with the topological insulator, many interesting physics can be exist. So it's also a very interesting topics, but I'm a little bit doubt we can make some commercialized product with the topological insulator. Okay, and another one is very important thing is the neuromorphic devices. As you know, the most important technology is AI, artificial intelligence. And in AI, there are two approaches. One is the von Neumann approach. The other one is non-von Neumann approach. Means based on current CMOS technology, people making some algorithm to develop the AI. And in other approaches, we can make some chips, which one is properly working for the AI. That's what we call the neuromorphic devices. And very recently, actually in the last year, one guy proposed the P-bit computing. This is also very interesting computing technology called the probability bit. With the P-bit computing, they can replace some part of the quantum computing. You may heard about the quantum computing, and quantum computing is very powerful for certain problems. And P-bit also do something like that, but it's much simpler and it's not difficult to implement. In first, their paper appeared about maybe 2 years ago as a theory, but after 1 year, they showed the realized operation. And also, we cannot ignore the classical magnetism like permanent magnets and the motor design motors, especially for the permanent magnet. We still using we have some idea called the exchange spin magnet, which one is kind of nanotechnology, because we combine the soft ferromagnetic and hard ferromagnetic layer with the proper combination. We can enhance the performance of the ferromagnet a lot. So if we can successfully making this kind of a new permanent magnet, we can make cheaper electricity and more powerful motors. It's very important in industry. Okay, first, SOT devices. As we already explained, the domain wall can move much more effectively with SOT compared to the STT. So the modern domainal device is all based on SOT, not the STT. And SOT, it includes the large wide FAT and spinal FAT and the DMI, which one I explained in the last class. And SOT name, here is the SOT name. The structure is a little bit different from the conventional name, conventional STT name. We have such kind of two phenolate layer. And when we read the signal, we can send in current this way. So we can using the TMR, there is an insulate MGO layer. So we can read the signal when this phenolate layer, one station is parallel or anti-parallel, they give a large TMR. So we can read it. And how we can write it? STT can send in current to this way or the other way. So the current must passing through this insulator layer. So there is a lot of chance of the breakdown. So there is some limitation of the sending current. But SOTM name, the current is passing through something like this way. And then the spin current can inject it to the ferromagnetic layer. And as a result of this injection current, the magnetisation can be switched. So main benefit of SOT is there is no breakdown in the insulator. And switching, actually I didn't mention about more details, but SOT switching is much faster compared to the STT. So we can achieve a very fast switching, means we can make a fast memory. And in the sense of the energy, it's more efficient compared to the STT. But the main disadvantage of this SOT is they occupy the large area. So that means it's hard to make a dense memory. So people try to use it for specific application called the logic memory. So what is the logic memory? The first, you should understand the memory hierarchy. Have you ever seen this kind of figure called the memory hierarchy? There are several memories. And top, this is the speed. In the top place, we need a faster operation. And in the bottom, the cost is cheap. So that means if we're making some kind of memory with bottom part, the cost is cheap, but it's slow. In the top part, the cost is expensive, but it's very fast. So you see here, super fast and super expensive, and the capacity is very small. But here, slow, cheap, but large capacity. Okay. So what is this? Here, mechanical hard disk drive, which one is very slow and cheap, but we can achieve a large capacity. So compared to this one, we have a solid state drive, like a SSD. It's a flash memory-based memory. And then there is some called random access memory, DRAM, or called the main memory of the computer. So this is the actually, this is the hard disk drive or portable drive, and this one is also similar concept, but it's a little bit faster, but still expensive. And DRAM, okay, DRAM is one of the main player of the physical memory. And also there are other kind of RAM called SDRAM, SDDRAM, and many things. And when we buy a new computer, the hard disk drive or solid state memory is orderable like 1 terabyte something. In hard disk drive, maybe it's that's the typical one. Maybe for the hard disk drive we have a 4 terabyte something. So you may store the kind of video or movie in hard disk drive, but you want to store your Word file or PPT file or your homework maybe in this drive because it's much faster. And main memory of the computer is like your desk. This is like a shelf of your shelf of your room, and there is some desk. So when you need something to work, you can bring some books from the shelf to your desk, and then you can open up the desk. Okay. So when you using this main memory during your process, you can easily access your data in your memory. And this part is CPU. In the CPU, there is several levels of cache. There is a level 1 to 3. So this memory, the capacity is very small, but still CPU using this cache memory they can access this cache memory very fast. And if you buy when you buy a new CPU, the more expensive CPU has a large cache memory. That means the performance can be good. And then in a CPU, there is a very temporary memory called the register. When they operate some kind of large operation, they should store some information a very short time. That's what called the register. So there are all these kind of things are memory. And as I already explained, this one is most expensive, but it should be very fast. And then and so on. Okay. So far we explained about this one. This is a kind of a standalone STT memory. But there are some kind of other memory which one is played very important role in a modern electronic. Yeah. For example, here in a modern computer architecture, the dedicated memory means the memory is physically separate with the logic. So when they operate something, we need to read the memory from your memory device, and you have to write the memory to here. This part, the read-write with the memory, is actually really spend a lot of time. So when you read your main board or memory spec, there is some kind of a memory channel or some speed of the memory. So for the fast operation, fast calculation, you need to make it fast. But there is some limitation because they are physically separate. So there's another idea. The memory is embedded they combine the memory and the CPU together in a same place. So for example here, we have a logic and memory. There is some kind of a data transfer, and it takes some time, and it's kind of bottleneck. And also in memory, we are using the DRAM. Then there is some leakage current. And the idea is we can making the logic and the memory together, all together. So if we're making this one, then we can make a much better logic devices. Then maybe students have a question. Then what's the difficulty of this part? The difficulty of this part is in a DRAM, as you remember that, there is a large, very deep trench that requires another technology. So they cannot combine with the CPU. It's totally different process, but MRAM or SDOT RAM can be combined with this logic process. So if you can make a combined logic and memory, we can make a much better and much faster CPU. So that's one of the main approaches. And the SCOMMUNIS is, I already explained about the SCOMMUNs in last class. It's called the SCOMMUN-based logic, memory, and neuropic and extra. SCOMMUN is very small, can be very small, like a 10 nanosec, and 10 nanometer. It should be meter. And stable because it's topologically protected and easy to move with a small field and the current. So there is some idea of the SCOMMUN-based operation. This is an information carrier, but also they can do some kind of logic operations, and they can make a rest memory with SCOMMUN and so on. So, but still, after finding this idea, people try to make good SCOMMUNs, but there are many open questions. The reading of SCOMMUN is another very difficult task because it's very small. That means signal is very small. And it should be stable, but when we carried out the experiment, the SCOMMUN can be easily destroyed and easily trapped in a defect. So that's the question. Actually, SCOMMUN should be very stable and they cannot be pinned by small obstacles, but truth is they do. So why that happens? We are still struggling to find the reason. And the small SCOMMUN is also another important question. When you calculate it, it can be very small, but the largest SCOMMUN can be easily generated, but the small SCOMMUN is not easy to generate and stabilize. So there are so many open questions, but it's very interesting for the future study. And magnonics is the kind of technology similar to photonics. So spinwave can carry information. So because it's based on the wave, we have using the advantage of the wave's nature, like interference. So we can make some kind of a new concept of devices by using the interference and reflections and many things. And also, you can easily modulate the frequency in a gigahertz range. The frequency can be modulated easily by the material constant and also the external field or current. So here, for example, there is some kind of excitation of spin wave, then spin wave traveling through the channel. And then if we have some kind of device for the amplification, we can amplify the spin wave again, and then you can detect something. So during this process, we can add or extract the wave packets like by the kind of logic operation. So the spin wave device based spin wave based devices also very beginning stage. So there are many things we can do. And also I explained about the neuromorphics. The neuromorphic device, this cartoon explains what is the neuromorphics. There is some kind of the biosystems, and the scientists want to making very similar things. Yeah, it looks like similar, but the important thing is the functionality. It doesn't need to be same. For example, when people mimic the wing of the bird, people invented the wing of the airplane. But the wing of the bird is much more complex, but the wing of the kite is very simple structure, because they just took very most important feature of the bird's wing. It's same. In a neuron system means we can mimic some functionality of the neuron system, not all the part. Then why we need such kind of things? For example, this graph means the von Neumann machine means the modern computer. Means the CPU plus memory structure. So when the problem is simple, this is the complexity of your problems, and this is the complexity of your computer. They have a kind of a linear behavior. Your problem is getting complex, your machine must be complex. But in this kind of neuron system, even for the simple task, we need a lot of machine complexity for the neuromorphic approach. But in a certain point, the neuromorphic system, the complexity is required complexity for the complex problem is getting lower. So this graph implies we need something here, because we are not handle the complex problems. The most simple example is the image recognition. When people are watching some photos, we can easily recognize that it's the cat or dog or human being or car or bus, or even you can easily recognize the brand of a car. But for the computer, that's very difficult. For the human, that's not easy. That's not difficult one. For example, just the matrix operation, like a very large number of large scale of the matrix operation. For the human being, it's really difficult task, but the von Neumann machine do it very easily. But for the image recognition or pattern recognition, it's very difficult for the von Neumann machine. So people start to study how the human being's brain works, how we can distinguish your friend from other people, how we can decide by watching the backside of your friend, you can recognize, oh, he is my friend. But we may catch some kind of very small part of information, but that's enough to recognize the people's identity. So there are many possible applications of that kind of approaches. So we need such machines. So, but still, this von Neumann machine is not fit well for that kind of purpose. So we need such kind of neuromorphic machines. So for example, in a neuron, this is the structure of neuron. And there is some kind of neurons, then they sending signals through this I just forgot the word, sorry. Anyway, so when they receive the signal from the outside, they do some kind of process, and then when the signal is good enough, they sending signal to the next one. Yeah. So this receiving signal part can be done with GMR or TMR devices or with the microwave detector. And the operation or process can be done by the microwave oscillator and some kind of binary memory structure or stochastic devices. And then sending the signal through the synapse means when we sending the synapse, we give us some kind of weight in our information. So we need a kind of memory store. So these small blocks is what we need to mimic the neurons. And fortunately, we all have such kind of device. For example, for the detector, we have a GMR and TMR. We can detect the magnetic signal. And also we have a binary memory by the making such kind of trilayer structure. And also I didn't mention it, but we can make stochastic signals with this structure. And also we can make the microwave generation, and we can make a spin wave emitter, we can make a microwave detector, and we can make a MEMS. All these things can be happens by the spin-based devices. All these small building block, we already make it. That means if we combine those nano devices, we can mimic the neurons. So people are actively doing such things. Okay, so let me make the conclusion of all these lectures. Spintronics was born in a late of 1980s. The reason the Spintronics can be born is at that time people making the superlatives means we can make some kind of layer structure, AB, something like that. And this length scale can be nanometer. Yeah, the length scale is very important meaning physically. For example, when you think about the anti-reflection coating, if you have some glass, and if you add some very thin diameter layer, reflective index of n, and the thickness should be order of lambda for 4, lambda of 4. This quarter of the lambda is very important thickness scale. So that means, when the thickness meet this kind of special thickness, we can make enhance the reflectivity or suppress the reflections. The important thing is the lambda, the wavelength of your light. When you're making this kind of layer structure, you have to control the thickness in order of a few percent of lambda. To make a large thickness, you cannot make good optical devices. So for the optics, you need to control the thickness order of lambda. But in a magnetism, the most important thing is exchange coupling. And they can happen order of nanometer. So when we adjust the thickness in a scale of nanometer, there are many new things happens. Okay, so here the important thing is exchange and the spin diffusion length. So when we shrink down the scale of the length below this kind of two very important technology, then we can make the new kind of materials and new phenomena can exist. So that means at that time, people start making such kind of new structure, which one is never existing in nature, so they can find the new phenomena. For example, quantum Hall effect and many new phenomena can be found in new materials. So that's why we are seeking the new materials in our department. Okay, so there are many new physics was involved, embedded like interest coupling, GMR, TMR, and speed sensor torque, spinor torque, spinor impact, Rashba, DMI, etc. All those new physics paved a new way of the spin-based devices. And then there are many new applications was also born. Okay, so let me make close this class. The future of spintronics is good or bad? Yeah, nobody knows. It totally depends on you guys, the young researchers. And not only this spintronics, all engineering part in current stage, they are all same problem. We are now living in a very matured technology period. For example, in a silicon-based semiconductor, Yeah, they are really close to the limitation. And also, for example, hard disk drive, the capacity is no longer, it's very hard to improve it. And also, display, for example, yeah, if you're making people, TV, they broadcast many CF for the new version of TV, but the quality of the screen is already limited. Yeah, in most of the people in usual people's eye cannot distinguish the difference between the top high-end screen and the middle level screen. Yeah, just imagine the speaker. If you buy like $100 of a speaker, sounds quite good. If you pay like $1,000, yeah, you can buy a big better speaker. And if you may spend like $10,000 or even $100,000 to buy your speakers. But what's the big difference? Yeah, if you are expert in the music, maybe you can see some difference. But usual people, it's very difficult to distinguish that kind of difference. So the problem is, if you make even better hardware, there is no big difference. For example, in a smartphone, yeah, few years ago, every month or every 6 months, new smartphone has equipped with more high technology, and the performance is quite different. Nowadays, the high-end smartphone compared to the just common, the difference in, yeah, there is some still big difference, but the feeling of ours is not quite big. So people hesitate to spend more money to buy a good product. So that problem, most of the engineering part. So we have to overcome that kind of problem by invent totally new technology. Otherwise, it's not easy. Okay, so anyway, so it's not only our problems, but all engineering problems. Okay, that's my final comment. Yeah, now I think it's good time for the questions from students. Yeah, you may ask any kind of questions, not only related to the lectures, but maybe any kind of things like physics or yeah, anything. Please ask me any questions. Okay, yeah, that's a good question. Actually, I said the final exam will be open book, and also if you may bring your notebook, so you can take a look the equations on my lecture note. So actually, it's exam, so I should ask some make some problems based on kind of equations. So if you have your lecture note, you may do it. But if you don't understand, yeah, it's not exactly the same one, but I just little bit twist the situations. You should understand, but the detailed mathematics is not that important. If I wanna see you understand the procedure. Yeah. Actually, I didn't understand what's the exact meaning of local effective field. Taeyong, can you send me that part? Then I will gonna answer you. But in my opinion, the kind of local effect field means, yeah, usually we are talking about the macro spin model. So there's no meaning of local, but in reality, the magnetic property of your sample can be varied by place. In that case, each place has a different local effective field. That's what I thought. The one chance question. Actually, the RKQI interaction itself has a much broad meaning. The exact meaning of RKQI interaction is the interaction between the S electron with the localized D or F electron. And then in this interaction, the spin polarization direction can be changed by the distance between them, and then the interaction stress is getting decreased by increasing the distance. That's the original meaning of the RKQI interaction. But the interwave exchange coupling is special case. Original RKQI interaction means it's point localized electrons in a three-dimensional space. But in interrange coupling, we are thinking about the layered structure. So in interexchange coupling, there are many atoms in an interface involved that kind of interaction. So interexchange coupling means the sum of all these point-by-point interactions. So as a result, the coupling is varied with the distance in the thickness of the spacer layer. So it looks like a RKQI interaction. That's why people call this the RKQI interaction. But the truth is that is the correct name is interlayer exchange coupling. No, you don't need a calculator, but you may bring your notebook. So yeah, but anyway, so you don't need any numerical calculation. Just a moment. No, this is only for the spin transfer torque, not without any external magnetic field. The domainol is moving by the spin transfer torque. Yeah, we are sending the current. Actually, I didn't mention that in this direction. We are sending current to these directions. So the domain wall feels some torque because of the STT. So that's why they are moving. Yeah, this is the current induced domain motion, the base of the current induced domain motion by the spin transfer torque. Okay, the 원창, the orbital quenching means in a 3D metal, the orbital means, for example, you have a atomic structure like this, and here. Yeah, if we have this atom, if we have a certain angular momentum of the orbital, usually they have in a top view, let's see. In a d orbital is generally formed something like this. And then in that case, when we taking look only this part, they have a strong asymmetry for this direction and this direction is quite different. But when we think about the interaction in the other one, for example, then this kind of symmetry, the asymmetry is reduced by this part. And that means they are all similar to, they have a kind of they lower the symmetry. So that means the angular momentum is getting smaller. So the average angular momentum in atom is almost zero. That's what we call the quenching. Yeah, you may take a look the any kind of solid state book about the orbital quenching. Yeah, and this orbital quenching is important in a 3D metal because the d electron is localized in a 3D metals, but still they can see outside. But in a 4D or 5D metals, the 4D or 5D or the F electron is very localized, so they cannot touch the outside of the atoms. So they still have a large atomic feature. So that means their angular momentum is not quenched. So your question is about the band structure things, right? Okay, here we think about the interaction between two atoms and the wave function. Oops. The wave function of this interactive atoms is can be expressed by the linear superposition of the two separate the wave functions. And in this calculation, what we need is this part. This is the definition of the Hoping matrix, and that means the overlap of wave functions of the atom number 1 and 2. So if we have one wave function here and the other one is here, beta is determined by this overlapping part. So in other words, means the electron is from one side, electron is moving to the other side. Means there's hopping. So the hopping integral, hopping matrix, hopping in sometimes also we say hopping energy is physically almost a similar meaning. If we have a large hopping means they can easily moving from one side to the other side, and that means there is a large overlapping of the wave functions, and also that means and this hopping element will determine the bandwidth and many things. So this wave overlapping of the wave function is very important concept in a band structure. So here this beta value is determined, for example, here the bottom and the top is in this case is 4 beta in 2-dimensional case. Sorry, this is for the 1 dimension. This is 1-dimensional case. So the theta can be plus minus 1. So the top and the bottom band is plus 2 beta and the minus 2 beta. Is it enough or you need more? Okay. Dongmyul's question is about the domain the domainal structure in detail. Actually, we already, I'm sorry, we only gave a lecture about the domainal in a non-wire structure. But in thin film structure, there is something more. There are many things can be involved in that kind of structure. So in 2-dimensional case, domain structure can be kind of a dendrite structure or a circular domain, and there are many chances. And as I mentioned many times, all things about the energies. So when we have a 2-dimensional system, there are the dipole interaction plays very important role. That means if we making the how can I say? Okay, when we are talking about the domain structure, maybe I can show this. Just a moment. Yeah, here I'm talking about the formation of the reason of the formation of domain. In order to reduce the domain, the total energy, especially the stray field, means the magnetostatic energy. They form the multiple domains like this, and then they make finally multiple domains in without any external magnetic field. Then this domain structure should involve the domainal energy. The domainal energy is kind of surface energy, or in other words, is positive energy. So that means if you make the large domainal area, the energy is increased. So the system will shrink down the domainal length or domainal area. So that's why they form like a circular domain, because with the same cost, they can spend more effectively the large area. And so the domain structure will be determined such kind of domainal energy compared to the reduced of the damage pole energy. So for example, if you have a strong anisotropy and a strong exchange energy, the domainal energy is larger. So that means they wanna making large domain to reduce the domainal area. But if your domainal energy is small, then you can making more area of the domain, more domain area, because the cost is not so high. But if you're making small domain, your dipole energy is getting smaller. So that's the competition between the dipole energy and the domainal energy will determine the minimum domain size. So this minimum domain size and the domain structure will be determined. The ms square means the magnetostatic energy, and the anisotropy energy, and the exchange energy. Yeah, that's my explanation. Any other question? Okay. If you don't have any more question, let us close today's lecture and final lecture of this semester. And we can see in next Wednesday morning, and I noticed the place and the time several times in LMS and in our talk. So anyway, if you have any question, you may ask by email and KakaoTalk. Okay, so have a good luck and see you in Wednesday in offline. It's our first time offline meeting. Okay. Okay. Bye.